So, can people, I actually haven't been working on finding new seeds, so does anyone have a nice solution where they got a better segmentation than this? Well, that's sad. Well, anyway, I think the Hoff transform is a really good idea to do the seed finding. Another one is to do very high width blurring, so do a Gaussian filter of, say, radius 20. And then you're going to get like a big spot for every coin and find the maxima there. And then just add one more seed outside. And I think that should give you a really good watershed segmentation. So if you're curious, you can try that out later. And so down here, I just have what I said earlier. Both of these methods, when you're trying to do real segmentation, and have a complex scene with all sorts of stuff going on rather than some nice round blobs. You want to do this type of approach as your initial segmentation and then merge the resulting segments together. And so right now we have a GSOC student, Vignesh Birodkar, and he's building those things into Scikit image. Yeah, but there's lots of libraries out there that will do these sorts of things. Oh, and the last thing you want to do if you're interested in segmentation, there's a thing called the Berkeley segmentation dataset, and that's the gold standard for measuring your segmentation ideas. So look for that if you're interested. Okay, so now we're going to do a couple of advanced examples. Go back to your index. The first one is fluorescence intensity on chromosomes. And what we're going to do is see how we can use some of these primitives to get rid of some of the noise in our source images and measure what we want to measure. So the basic question that we want to ask here is, so this is a real image. And what we have is chromosomes and the centromeres, which is the little bit of the chromosome where, if you haven't seen a chromosome, it looks like an X. They sort of tie together. In green, you've got the centromeres, which are part of the chromosome, and then in blue, you've got the rest of the chromosome. And in red is the protein that we're interested in. And what we want to know is, does the red bind differently in the centromere versus the rest of the chromosome? And the big challenge is you can see the illumination is really uneven here. And that has to do with just the way the image was prepared. And so it's very hard to find the chromosomes reliably. If you're going to find this chromosome here, which is very, very dim, all of this stuff is going to be really blown out, and you're going to get a lot of stuff outside the chromosome. So we'll see how that goes. So usual setup, nothing new there. And then we just load the image, and here's the image with the color histogram. This is the same thing as roll axis. I'm putting the last index first, which is the channels, and then 0, 1, the first and second channel, first and second dimension. And so that gives me, by iterator unpacking, gives me my three things of interest: the protein that I'm measuring, the centromeres, and the chromosomes. So I'll do that. And then we're just going to threshold just to show you how it works. I think I need to... Yep, okay, so for the green image, you can see that it's very nicely peaked. So there's virtually no noise, and so the thresholding works really well. You get all of the green centromeres are found easily. But for the chromosomes, it really does not work at all. So you can see over here, again, this is the cube helix, which enhances the contrast a bit and lets you see all of the different levels of grayscale. So this chromosome, you can see, is a little bit cut off, and then where the chromosomes are a lot brighter, you just get this big blobby mess. So there's a thing called adaptive threshold, which Scikit image has. And all it's doing is it's doing something similar to Otsu, but it's doing it in a little window. So for this pixel, let me look at this neighborhood. Let me build a local histogram and find the cutoff point there. And you do that for every pixel in a sliding window throughout the image. So we do that, and you need to define what the neighborhood, and here I've picked 51. Looking at this image, does anyone know why I picked 51? It's not a bad idea. Yeah, sorry? So it's the width of the box that you're going to be using. And yeah, it's essentially the width of the chromosome. You want to make sure that it's small enough that you don't threshold, you don't do a global threshold, which we saw doesn't work. But you want it to be big enough that it captures a bit of foreground and a bit of background every time. So that's the basic idea of a block size. Okay. By the way, this is a real research example. So when I first got this, I was like, what the hell? And I think this is just some interference pattern that has to do with the way the slides were prepared. So the exercise is, how can you fix this? The goal is to, you can see the chromosomes, they're all there. So the threshold adaptive worked, but you've got all sorts of other stuff that you don't want. Using what you've learned in these tutorials, how would you approach this? You don't need to get individual chromosomes. You just need to get the foreground and the background from the chromosomes using this adaptive thresholded image. And we'll be going around. You can see what you want to try. Does anyone else want a bit more time and a bit of a hint, or should I move on? All right. Okay, so I'm just pasting my solution from earlier. So I just made a diamond of radius 4. I think it would work equally well with a disk. And then you do an opening, right? And the reason that this might work is because you have these big regions and they're connected, so you can't just get rid of them by size filtering. But they all have this dark speckle through it. And so when you do an opening, you get the dark speckle expanding. And if the opening is big enough, then you get rid of all the white speckle around it. Whereas these chromosomes are nice and solid, so the opening will not get rid of them. Just like you maintain the C when we did the very simple small opening example. Here the chromosomes will be maintained. And the other thing is, you'll see, and this is something that I got through experimentation, you get some small islands remain from the opening, and so, but they're smaller than the chromosomes, so you can exclude them using the remove small objects function, which expects a bool array, by the way, so that's why you need the S-type bool here. And so I get rid of anything smaller than 256 pixels in size. And here's what I get. Okay, so this is the original image. This is the adaptive threshold, as you saw. If you do an opening, again, you need to experiment with the right size. You get rid of most of it, and you just have a little bit of the speckle remaining. You do a remove small objects, and you get all of the chromosomes back. So you see you even get this dark one, and you get this bright one, and both perfectly. And so now that we've done that, the key is you can work through these as if they were NumPy arrays, and all of the NumPy, SciPy, Matplotlib functionality is there for you. So basically, I want to get all of the protein intensity at the centromere, the protein intensity on the chromosomes outside of the centromere, and do a histogram of that. So again, we do this with, yeah. You should just use a disk. I can't think of one, but I'm sure there must be. I use the diamond because that is what comes naturally in SciPy. SciPy doesn't have a ball structuring element, or they didn't when I started working on this. So that was the only reason, and then I stuck with it because it worked really well. Yeah. So the reason why you want to use the disk is there's no specific reason that this direction and this direction should be special relative to that direction, right? If they were in some way special, then yeah, you can use the
So in Scikit image, it's all treated equally, but in SciPy in the image, the square or rectangle elements have really fast paths, whereas circular disks with like.
All right, I didn't know that. There you go. Okay. Any other questions? So the distinction is SciPy, I guess it's a much more mature library, so the path evolution is a bit slower, getting new functionality and so on. So that was the idea behind the Scikits, is like fast development of new ideas. So Scikit-learn and Scikit-image, there's a couple of Scikit-bio are presenting this week, Scikit-fuzzy. Yeah, so the idea is things that are part of the SciPy ecosystem, but you don't want to wait for the SciPy devs to let you in. Which, SciPy is an incredibly big and well-maintained library, so I'm not saying that you should let anyone in, but if you want to do fast development, do it on the Scikit. And yeah, so some of the functionality will overlap, but the key idea is interoperability. So centromeres, what did I call it? Centromeres binary, right? Okay, so this is just giving me the array of pixel intensities in the protein image everywhere that a centromeres has been found. In the chromosome, the rest of the chromosome, I will use CHR1. Okay. And so then what we do is we concatenate the two, so we get just an array of... all right, so this is just so that I can get the minimum and the maximum of all the intensities to adjust the binning for the histograms. So what I want to do is compare two histograms, one of the intensities at the centromeres and another one at the chromosomes, and I want to see if they're any different. So that's what I'm doing. I'm just computing the bins that I want, and then plotting the histograms. In blue is going to be the centromeres, and in orange, the chromosomes. Right? And so obviously there's many more in the chromosomes, but you can clearly see that the intensity in the chromosomes has a different distribution from the one in the centromeres. And again, so the last bit of this example is not really about image processing. It's about getting what you want out of the images and doing the rest of your analysis in the scientific Python ecosystem. And so let's do the last example. If you go back to your index, it's measuring intensity and intensity profile. And again, it's microscopy, because that's just what I happen to work in. So the idea in this case was, this is the spinal cord in a zebrafish embryo, and it's been wounded. And the idea is to study regeneration and figure out what factors aid or inhibit regeneration of the spinal cord cells. And so what we want to do is we want to measure the intensity of fluorescence along the axis of the cord over time. We're not going to worry about time today. We're just going to worry about getting that measurement. So we'll read in the image. And as we talked about, getting the full SciPy stack, we're going to use SciPy itself to estimate the coordinates. What we want to do is figure out where the axis of the column is. So we're going to figure out the coordinates of the column here and here. So this is just setting up the plot, but basically we're going to do a Gaussian filter on the top part of the image so we can figure out the center up here. And we're going to do a Gaussian filter on the bottom part of the image and figure out the center of it here. Not just the center, but also the width. So first we do the Gaussian filter. So in blue is the original intensity, and you can see it's got like peaks and troughs, and then if you do it smooth, you get one smooth Gaussian-looking curve, and now we can estimate the position of maximum intensity and the width. So basically, I'm just taking the half of the maximum intensity and finding the width of the Gaussian in the middle. And then we will just take the maximum of the two widths if they disagree, which they do, but not by a huge margin. Yeah, so this is your position at the top, it's the 421st column. It's 181 pixels wide. At the bottom, it's here, 730. So you can find it in the original image as well, over here. And the width of 142. So we're going to take 181 width. So then under measure in Scikit image, so just import the measure profile, and we can, oh, I left that as an exercise. You will fill in the right parameters for profile line now that you have the width, the top location, the bottom location. So you can find out the doc string for this just by using IPython's question mark. Nope, no you can't. Really? I was under the impression. Oh, really? All right. To be fair, they're pretty magical. Okay, so here's the doc string, so you can figure out where you want to measure from and to in the image. Oh, that's interesting. I think that should work. Okay, so if everyone hasn't done it, so you just pass it the image, the source coordinates. Again, this is NumPy indexing. The destination coordinates. I'm not sure if you can just use -1 indexing. I think you can't. So you have to give it a specific, this particular code. The -1 indexing? Yeah. Yeah. So that would be a nice pull request. But anyway, so you have to give it real coordinates. That's the bottom mode. The width, and then this is just the interpolation mode because it might end up measuring some pixels outside of the image. And the question is, what do you do with those? So I've chosen reflect, which just means that it's as if there was another image that's the mirror image of your original when it goes outside. But it's not a big deal. Basically, it only affects the very edges of your measurement. And then we can just plot that. And that's the trace. Okay? Let me just get rid of this. So again, it's not, this was a simple example, but it's just meant to illustrate the advantages of working in the SciPy environment and just getting all your data directly as NumPy arrays. And that. Any questions? Yep, so that's the end of the tutorial. If you have your own images that you want to fiddle with, we have a small amount of time. We will hang around and answer questions. Yeah? No, you'll have to build your trajectory. But that's a cool idea. Yeah, so if you have your own images, we'll stick around till time. Yeah? Yep. I'm uncomfortable dictating that. So our BFDL is Stefan van der Walt, who could not make it this time. Yeah, I don't know where he's. Basically, it's driven by the community. So if you need something, and it's general enough, it's probably in scope. And you can contact us, you can submit an issue. So over here, you can follow us on GitHub. We have a mailing list, and it's very active. We always have discussions there about whether this function or that function should go in. You can contribute your own stuff. So it's usually, we have high standards for code quality. So basically, stick with it, don't get frustrated. I found it really rewarding. I actually started coding for the package because I came to SciPy 2 years ago. And I think it's basically worth it because we have really nice documentation, really nice code. Very nice to maintain. So that's a good point. Let me just finish this. So contribute, and also we have a paper that just came out, so we're very excited about that. So let's go to the website. Hopefully it'll load. This isn't our site. This is the hotel network. Okay, so, oh, and if you go, so this link for contribute, it has the guidelines for new contributors. Again, so we have high standards, but we will guide you through it. So if you want a feature and you feel like you can implement it and it'll benefit like tons and tons of other users, submitting to Scikit image is the right thing to do. So if you go to the website, you've got the API. So if you've got the documentation, which includes all of the functions, including a big list of all the functions. So that's usually where I go to if I'm wondering if I can do something within Scikit image or what exactly is the syntax that I'm looking for. And we also have a gallery with lots of examples showing you how to do all sorts of stuff. So in particular, and the other cool thing is, yeah, these are generated every time we make changes to the code. So they're very up to date with the latest stuff in Scikit image. Sometimes too up to date, because you'll notice that it went directly to the development version. So we often get messages of like, hey, that's not working. But yeah, so here's all of the examples. One particular one, if you look for morphology, there's a longer morphology sort of walkthrough in the website, so you can explore the same ideas that we talked about using this example image, which is sort of an idealized version of having some objects in the image and so on, of different brightnesses. Yeah, so this is if you're wondering how to do something slightly more elaborate, there's a good chance that we'll have something useful in this gallery. Anything else? Okay, well, as I said, I at least will be here till 5 if you have random images you want to show me, or any more questions that you want to take offline. Thank you.